Webcast is now starting. All attendees are in listen-only mode.
Hello everyone. Welcome to our webcast, Medium and High Voltage Circuit Breaker Testing. Today we'll be talking about the different circuit breakers in medium and high voltage substations, how to prepare an appropriate test plan according to manufacturer specifications so that your circuit breaker will never fail to operate. My name is Yerto. I'm the Marketing Communications Engineer for Mega North America. I'll be acting as the moderator for today's presentation. If you have any technical issues or questions for our presenter during the seminar, I will be supporting you. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the highlighted box in red. You may also notice that there are two audio options, telephone and mic and speakers. The mic and speakers options uses voice over IP, so you may experience intermittent audio lag due to bandwidth. At any time during the presentation, you can switch to telephone audio option. You will receive a copy of the presentation afterwards, and remember, you can ask questions at any time during the presentation, and I will interject them as we have time. Our presenter today is Robert Foster, Applications Engineer for Mega, specializing in high voltage circuit breaker and transformer testing. Robert is based out of Paradise, California. Thank you for joining us, Robert.
Thanks, Yer. Good morning, everybody. Thanks for being here with us this morning. Before I start, this is about medium and high voltage circuit breaker testing, but I always like to make a little distinction here between low voltage circuit breaker versus medium and high voltage circuit breaker. With low voltage circuit breakers, these are below 1,000 volts, and they'll trip on their own when there is enough current put through them. So the timing test is actually performed at real live currents, where you inject current through the machine, and it actually, depending on the type of test you're performing, it'll do a electromagnetic trip or a thermal trip, but it'll trip due to the current going through it. Medium and high voltage circuit breakers, on the other hand, these are breakers above 1,000 volts, and they can't trip on their own. They need to be told from the protection circuit or whatever that they need to trip, and then you give some operating voltages, current flows through the trip or close coil, and this is what operates the breaker. So these are tested at low voltages, low currents, with a time and travel analyzer. So what we'll talk about first is the types of circuit breakers we can see out there. And after that, we'll go on to time and travel analysis. But first, we'll talk about live tank and dead tank circuit breakers. And you'll notice that both have very similar insulated mediums. You can have vacuum in live tank, you have vacuum in dead tank. In live tank, you'll have something called a minimum oil circuit breaker, whereas dead tank, you'll have something called a bulk oil circuit breaker. There's something over in the live tank called air blast that there's nothing analogous over in the dead tank circuit breakers. But you'll both have SF6 circuit breakers and circuit switchers in live tank. Then you'll have dead tank, GIS, or hybrid type circuit breakers over in the dead tank realm. So what do I mean by live tank and dead tank? Live tank circuit breakers means that the actual interrupter, the tank housing the interrupter, is at line voltage. So you'll see up here that this switch or the circuit breaker, the interrupter, is inside here, and you got high voltage on both sides there. And during operation, this tank is at line voltage. Dead tank, on the other hand, is where the interrupter is in a tank that's grounded during service. So during service, you can come up, and I don't recommend just hanging around circuit breakers while they're in service, but you can theoretically come up, touch this is ground, and you're perfectly safe. So what do we have in different types of circuit breakers? One thing to consider is the number of breaks per phase. You can actually have anywhere from 1 break per phase, and so a total of 3 breaks, 1 for each phase, up to 16 breaks per phase. So as the voltage increases, the number of breaks increase as well. As you'll get up to maybe 1 or 2 breaks, or 1 break from up to like 245 kV, and then as you get up to 362 kV and above, these numbers start increasing. And in some of the older breakers, when you get up to the 765 kV, you could have up to 16 breaks per phase. Now, when I talk about breaks, these are the main contacts. You can also have a resistor in there, And so you could theoretically have 16 main contact breaks and 16 resistor breaks per phase. Now, a dead tank circuit breaker, from the field testing perspective, you only have one break per phase. You go off, you'll just see the bushings and hook to both sides. But internally, these can actually have anywhere from 1 to about 4 breaks. Same thing with bulk oil circuit breakers. From a field testing perspective, they're 1 break per phase, but they can have multiple breaks inside. Live tank circuit breakers, on the other hand, you get to see how many breaks they have right there in the field, and you can test each break individually and hook up to them. So here's an example. On the left, we have a dead tank circuit breaker. So you have your 3 phases, and the tanks are kind of hidden by the cabinet, but your 3 interrupters are there. And that's 1 break per phase. On the right here, we have a live tank circuit breaker. And so now voltage comes in here, goes down, comes out here. And so this is live tank, but 1 break per phase. Then as we start getting into 2 breaks per phase, you'll see that in the field, these are all live tank circuit breakers. So this one, you have 1 interrupter here, another interrupter here, times 1, 2, 3 phases. Same thing here, 1 interrupter on one side, 1 interrupter on the other side. One thing I'll mention is you see this is a 500 kV live tank circuit breaker. And in the back here, you have a 500 kV dead tank circuit breaker. And so this probably has at least 2 breaks per phase internally. But from a field testing perspective, you can see the one side here, and there's 1 more bushing over here, so it looks like 1 break per phase. Then, as we keep going up in voltage, and these are some old air blast type circuit breakers, you can see we have 1, 2, 3, 4, 5, 6 breaks per phase. And then over here, we actually have a 10 break per phase circuit breaker. You can see 1, 2, 3, 4, 5, 6, 7, 8. And I didn't have a wide enough lens for this one, but 9, 10 on the number of breaks per phase here. So let's talk about the different types of circuit breakers out there. One of the most common types, especially for distribution voltages, is your vacuum circuit breaker. Now recently, these circuit breakers have increased up to about 72 kV in a dead tank design in the US, and in a live tank design, you'll see up to 192 kV over in Asia. One of the reasons that they're trying to increase the voltage here is, of course, these are a lot more environmentally friendly. But generally, in the U.S., you'll see them just for distribution around 15 kV or so. You'll notice I got a picture of the interrupter over here on the right. You'll see that's a very small distance between those plates, usually maybe 12 to 17 millimeters. And so when this interrupts, those plates separate, and there's not any gas in there to form the arc. It's in total vacuum. But the actual plates melt away a little bit, and that's what forms the arc. And then when they separate enough on an X0 crossing, that arc extinguishes. Vacuum circuit breakers have been around since about the 1960s, and of course they're still manufactured today. So the next thing we have is something called a bulk oil circuit breaker. So once again, this is a dead tank design, and now oil is the actual insulation medium, and it's used to quench the arc. It flows over the arc during operation, during interruption, and it extinguishes it. The same thing as I mentioned before, it can have many breaks internally, but from a field testing perspective, it looks like 1 break per phase. These things have been around a very long time, and I'm sure everyone has seen these in the field. Approximately about 50% of them are still out there. They were manufactured from early 1900s all the way up until about the 1990s. So they're no longer in production, but you can still get a lot of parts for them. You can still maintain them. And that's one nice thing is you can maintain these circuit breakers and keep them running, but they do require a lot of maintenance. So generally a lot of people are pulling these out when they come up for maintenance and replacing them with an SF6 style circuit breaker. So on the live tank side, we have the minimum oil circuit breaker. So these were designed to reduce the amount of oil that was needed, so you didn't have this huge bulk oil circuit breaker. Once again, these have been around a while, 1950s and 1980s, but as SF6 came in and took over, these were replaced with SF6 style circuit breakers. So same thing, you can still get parts, still maintain them, but once again, they require maintenance, and so they've opted to start removing these from service and putting in SF6 style. Something else you'll see out there is an air blast circuit breaker, where now compressed air is used to blow out the arc when it's interrupting. And these are the ones that you'll get many breaks per phase, 16 breaks per phase and beyond. But the nice thing about the air blast circuit breakers are they're really the ones that got us into the EHV, the extra high voltages, up to your 500, your 765 kV in the beginning, because they were powerful enough to interrupt those arcs. And these have something called post-insertion resistors in them. I'll talk about that a little bit later. They're very loud. When these things operate in the substation, you know it. I've seen just from the cabinet where the air was not properly vented out of the mechanism, I've seen cabinets blow out and different things from this. Same thing, manufactured 1960s to 1980, no longer in production due to, it was once again replaced by SF6 style. High maintenance, so these are once again being opted out and replaced with your SF6 circuit breakers. So the next thing I'll talk about is SF6 style circuit breakers, sulfur hexafluoride. These can come in dead tank, live tank, GIS, hybrid, circuit switchers. The original design from about the 60s to the 80s was a dual pressure design, and then after 1980 and on, they came out with this single pressure kind of auto puffer style design. So SF6 sulfur hexafluoride, it's a very nice dielectric. It has a very large withstand capability. Physically, it's 5 times heavier than air, so you'll see when you remove the gas, you pull it out with your evacuation cart and everything, and then you still open and you can still see a little bit pouring out if you didn't get in the pull vacuum long enough. One of the downfalls of this is it's a greenhouse gas. So its heat absorption is over 20,000 times greater than CO2. It's something like 23, almost 24,000. And this is, of course, environmentally a problem, but this is one of the things that makes SF6 gas such a good insulator, such a good arc interrupter. The gas itself is an inert gas, so non-toxic. It doesn't react with anything, but when there's a fault and you combine the gas with, if there's moisture in that circuit breaker at high heat levels, it produces some byproducts that can be highly corrosive. So if you have to go in and maintain a circuit breaker that's suffered a fault, or if you're working near the interrupter, near the arcing zone, the arcing contacts and the residue trap there, you have to be very careful and make sure you're dressing hazmat, you're not breathing this in, wear a respirator, different things like that, because it is a highly corrosive substance. So once again, dead tank circuit breaker, SF6 dead tank, means the tank's grounded in service, the tank that's housing the interrupter. So a couple advantages, you'll see the CT's mounted right on the circuit breaker itself. With all the weight being down lower to the ground, these are more stable during earthquakes. So anywhere where you have seismic activities, they might opt for a dead tank circuit breaker. One of the downfalls of this is it does use a lot of SF6 gas. So you need to, with all the regulations and everything, people might be opting more for the live tank so you have less overall gas in your system. That being said, in the U.S., this is the main circuit breaker that we see. We went from a bulk oil towards your dead tank SF6 circuit breaker. You still see some live tank circuit breakers, but mainly in the U.S., this is the one that most people choose. One other thing to mention is in cold environments, you can actually put your heater right on here to keep the gas from condensing, so you don't have to mix it with gas or anything. Moving over to the SF6 live tank circuit breakers. Once again, live tank means that the tank is live at line voltage during service. So these are very popular. You'll only see this, or in Europe you'll only see this style of circuit breaker. In the U.S. you'll see some of these here and there. As I said, the main is dead tank circuit breakers. Canada, Mexico, they're about 50% live tank, 50% dead tank. One thing I'll mention is these tend to have a lower footprint, because you can see you have a nice small footprint here, but if you need to put CTs, you have to put standalone CTs, so that really takes up the rest of the footprint there and doesn't give you that much of an advantage. And as I mentioned with the dead tank circuit breakers, you can actually put a heater on the tank itself, whereas these you cannot, so you have to mix it with either a nitrogen or a CF4. And if you do that, the circuit breaker must be derated. And this is to actually keep the SS6 gas from condensing in cold environments. Something you'll see out there is GIS, gas insulated switchgear. I kind of see this as a dead tank style circuit breaker, but with a disconnect switch, a grounding switch, maybe some PTs and CTs and different things, all insulated in SS6 gas. So where they use these, you can see the little guy here for reference, where you want to shrink a large substation down to a small building. And so anywhere where property is very expensive, so major cities, you'll see them in Seattle, New York, LA, Vegas, stuff like that, and land is quite expensive. They'll build these maybe underground or under a building, and so the public doesn't even see it, but you get a whole substation right in the middle of a city. I've also seen where they'll take it like a national park, and they got lines coming in and they need a substation, but they don't want to take a lot of area of the national park. They'll put a GIS system in there. So a large amount of SS6 gas is used, but it's a trade-off because you get the substation to shrink a lot.
Hey, Robert. Before we move on, I have a couple of questions from the audience. So Lilia would like to know who is the biggest manufacturer of SF6 high voltage breakers in the U.S.?
In the U.S., I would say it's kind of, we have a couple different manufacturers. I would say the main ones you'll see out there are, of course, ABB. You'll see Mitsubishi, Siemens, Alstom, HVB. I don't know who the biggest manufacturer is, but those are the kind of the main ones that you'll see out there.
Mm-hmm. And Chris would like to know if you have any suggestions for replacements for SF6 breakers that are 115 kV and above.
Any suggestions for replacements, like an actual? I don't quite understand the question. I mean, I don't. There's many different brands out there. I don't know what exactly that question.
Okay, no worries. We'll probably take it offline with Chris and email him later on. Thank you.
Sounds good. Mm-hmm. So now that we've kind of looked at the different types of circuit breakers out there, we'll talk about some of their components. What we'll see here is they'll all have some kind of insulation. They need control circuitry. As I said, these need to be told when to interrupt, when to close, when to open. They're going to have some kind of mechanism that drives the interrupter. So the mechanism actually it performs the closing and opening operation, and then the interrupter actually interrupts the arc there. Now, in certain designs of circuit breakers, you'll have some extra components, capacitors such as grating capacitors or shunt capacitors, and you also have resistors, and they might be pre-insertion resistors or post-insertion resistors. So the control circuitry, this is really just, it's a circuit that receives the open and close commands from, as I said, the external devices, from protection and control or wherever. You'll have coils, auxiliary contacts, alarms, limit switches, different things like that. It'll have, include the motor to charge the operating mechanism. And really, when you first get there, you want to look at your control circuitry, and you want to see, like, okay, let's look at the prints and see what we need to hook up to actually operate this circuit breaker to perform our time and travel analysis. So the operating mechanism, as I said, this drives the interrupter. This opens and closes the breakers. And you'll have many different designs. You have spring, hydraulic, pneumatic, magnetic. One of the most common designs is a spring-spring design. The reason we use a spring is because it's really the simplest mechanical device that we can think of. All you do is you charge this spring, and it's sitting there ready to go. The coil, the trip coil, will release the spring, and it operates. All you need to do is give it enough voltage to release that spring, and it takes over from there. And one thing to notice or to mention is on a spring-spring design, you'll have a closed spring and an open spring. So the motor will charge up the closed spring, and then once that closed spring operates, when it closes, it'll close the circuit breaker and it'll charge the trip spring as well. So the reason they do this is you're never without the ability to trip. If there's one thing this circuit breaker needs to be able to do, it needs to trip on command. You need to be able to at least do a close and immediately followed by an open to interrupt that fault in case you close in on a fault. There's a couple different designs or applications, I would say. When you have smaller voltages, maybe 245 kV and below, generally you'll have a gang-operated circuit breaker. So this means you have one mechanism that controls all three phases. And so it'll be close to one, and there will be linkages going to the other two. And then when you get to higher voltages or special applications, you'll have something called an IPO circuit breaker, or independent pole operation. This means you have an actual mechanism for each phase. So generally, your 365 kV and above, you'll have those. But where you see them at 245 kV below, it'll be at synchronous switching applications where you're actually closing, one pole like staggered, so you have it closing in at the zero crossing of each one, or opening on a reactor bank. And then on certain breaker designs, they might have a higher K rating of the breaker, and so the one mechanism isn't powerful enough to interrupt, so they actually make it an IPO style breaker. And then some other applications I've seen is where they might have it designed to where if there's a fault on the line, they might just trip one phase to clear that fault without interrupting the other two. So here's an example of a dead tank circuit breaker with a gang operated on the left. This is about a 121 kV circuit breaker, and this is a kind of an interesting design where you have all three phases in the one tank here, and this is an SF6 style circuit breaker. Then on the right, this is a 362 kV circuit breaker. You'll notice you have 1, 2, 3 phases there, and they each have their own mechanism driving it. Then coming over on our live tank design, same thing. You can have a gang-operated live tank circuit breaker, so you have one mechanism here in the center, and then there's linkages going, of course, over to the other two phases there. Then once we get here, of course, this is 2 breaks per phase, but you'll see we have 1, 2, 3 mechanisms, one mechanism for each phase there. So interrupters. The interrupter is what's responsible for extinguishing the arc. This thing is, we need to make sure, of course, the mechanism drives it, but if the interrupter isn't designed right, it won't interrupt the arc. For vacuum circuit breakers, you have 2 plates, and as I said, they're separated by a very small distance, but this plate is both, when it's closed, this is what's conducting the current, and then when it's opening, this is what's actually arcing and interrupting the current as well. So in a vacuum-style circuit breaker, it's actually both the main contact and the arcing contact is one contact. That are these plates. Now, SF6 has a different design, where you actually have a separate main and a separate arcing contact. So the main contacts are made for when that circuit breaker is closed. They're just there to conduct the current, have as little resistance as possible, and keep the current flowing without heat. And usually the main contacts are some kind of a silver-plated copper or something like that. Whereas the arcing contact, this is designed to take all the heat and all the energy during the arc and during the interruption process. So the arcing contacts usually maybe like a tungsten copper alloy or something where it can take this high amount of heat. You're getting very, very large amounts of heat in there. And so the arcing contact's actually designed to wear away in service and protect the main contact. And there's some tests you can do, such as dynamic resistance measurement and different things to check on that and make sure it's not wearing away too quickly. And this is just a little picture of the internals of an interrupter here, and you can see a couple of things. Well, one thing I'll mention too is you have generally a fixed contact and a moving contact in the circuit breaker. So one side sitting there just fixed, and then the mechanism drives the moving contact in and out. But here we have, as I said, the fixed contact. We'll have your arcing contacts, and then a main contacts on the outside there. And this is a standard design with the arcing contacts in the center. One other thing you'll see out there are capacitors. One thing is grading capacitors. So once you get into multiple breaks per phase, you're going to have capacitors over these breaks to even the voltage distribution across each break. You will see them. You can see them here. There's no moving parts. It's just mounted in parallel to the actual interrupter itself. You can always see these on a live tank. On a dead tank, as I mentioned before, you can have multiple breaks inside, and you'll have these grading capacitors inside, but you might not see them from a field testing perspective. Something else you might see is a shunt capacitor. I've seen even on the dead tank circuit breaker, on one bushing on the outside, they'll have a capacitor on there, and these are usually to help with improve the fault interruption ability of that circuit breaker. On the other side, you'll notice this is that same breaker, but flip around and they have resistor contacts on them. And the reason you can tell it's a resistor contact is it's actually connected through linkages down to the mechanism. So the resistors are operating during service as well. So we have two different kinds, pre-insertion and post-insertion resistors. So pre-insertion resistors are used on your closing operation. So when you have high voltages, long transmission lines, you basically have this large capacitor there. And so when you close that in, you're given a huge voltage spike to your circuit breaker. So what they'll do is they'll close a resistor in first to bleed off some of this energy. And then the main contacts will come in, which of course shorts out the resistor, and then that resistor will come out while it's sitting there just in the closed position. One reason an alternative to this is synchronous switching, where you have an IPO circuit breaker and you're operating each one at current crossing of 0. But this is more expensive and a little more complicated, so a lot of people just opt to put a pre-insertion resistor in. And generally you'll see these on oil circuit breakers, maybe above, like maybe the 169 kV and above. On SF6, you'll see them 365 kV and above, the resistors on there. Something you'll see on an air blast circuit breaker is called a post-insertion resistor. And this is when now the breaker is opening. What happens is the circuit breaker itself can't handle all the energy in the arc. So as it goes to open, this post-insertion resistor comes in to help bleed off that energy, so not all of it's going through the contacts there. It opens up, and then the mains open up, and the resistors and the circuit breaker interrupts the arc. Since these are on air blast, you don't see these on any modern SF6 or vacuum or anything like that. But it is something to be aware of and something you need to check if you're timing out in the field. So now that we have an idea of what types of circuit breakers are out there and some of the components that we're looking at, now we can talk a little bit about time and travel analysis. So we'll go over some setup, talk about, show a few examples of results, talk about conversion tables and speed calculation points. And one thing I want to mention is the importance of motion measurements. I see a lot of people out there that are just doing a first trip, not even doing timing. Then if they do timing, they only time the main contacts. But there's really, if you're out there doing the timing of the circuit breaker, you really want to hook up a motion transducer and perform time and travel analysis.
So, Robert, before we move on, can we answer a couple of questions from the audience? Gary wants to know, are pre-insertion resistors left energized when the breaker is closed?
So, no, the pre-insertion resistors, what happens is it'll come in and it'll close, and then the main contacts come in, But after the main contacts come in, even though it's technically shortening out that resistor will still come back out of this, or come back, out of contact. So only the main contact is actually engaged when that circuit breaker is closed. And this does add a little bit of complication to the internal designs of that interrupter.
Distribution breakers.
Distribution breakers, if it's mainly like a vacuum circuit breaker, if you look back when I was, one of the pictures of that vacuum circuit breaker that I had was that was a distribution type circuit breaker. You'll actually see it's a low voltage. You can see from the bushings and everything, the vacuum interrupters in there. So that's typically what you see as a distribution type. I've seen maybe like a SF6 circuit breaker that they're using at like 32 kV or something, but it's usually like a 72 kV design. They went down because they needed higher fault interruption current. You'll also see, and I don't have a good picture of one, but some oil circuit breakers that are a lot smaller. They're all in one tank that can be used for distribution type. But those are, of course, older design that are no longer manufactured.
Okay, thank you. We'll get to more questions at the end of the presentation if we have time.
So, all right, so when performing time and travel analysis, there's a few things. Of course, you need to hook up to the control circuit so you can operate the breaker, tell it to close, tell it to open. You need to be able to hook up to the actual timing terminals, or the bushings, so you can perform your contact time analysis. Then to the mechanism, you hook up your travel transducers, so you're getting the actual motion of that interrupter. And of course, if you're out there in the field, you want to make sure you always have your ground on for safety reasons. So, connection to the control circuit. I always recommend reading the print. Some people say there's some common connections such as 5, 7, and 9, but I never rely on those. I've seen stuff written in the cabinet and everything. I always verify the print. I always ask for a print because you don't know who wired or who did what. As long as you refer to the prints, you'll have the correct, well, hopefully you'll have the correct connections as long as no one's changed anything and not mentioned it on the prints. Timing lead connections, you can see up here, right? These are, once again, distribution type. So here's another good example. But coming in, you go on each side of the interrupter, so you have your 3 phases, and then you're going to each bushing there. And then up to this live tank, this is a nice example where you'd put one break here, a common, and another break here. So you'd record both these breaks on a single break per phase live tank. You'd put one up here and the other connection right there. Of course, the next thing and the most complicated thing with circuit breaker time, this, I wish I had an easy way to do this, but really each breaker has to be evaluated for its factors. Are very good about giving you pictures. Other ones, especially some older designs, you might have to figure out on the fly in the field. So I'll first talk about a linear transducer mounting. Here's an example on a bulk oil circuit breaker, and most of the bulk oil circuit breakers out there use a linear transducer. I have seen some rotary ones, but generally you can hook up this linear, and the nice part about it, if you see right here, you zoom in, it connects right exactly to the interrupter. So you're measuring a 1-to-1 ratio right on the stroke of that interrupter, so you know exactly how the interrupter is traveling. Now you might have something where you can't get directly to the interrupter on your SF6 style, so if they have some kind of little bracket that goes on the linkage here, and as this rotates, it drives your transducer back and forth. So this actually acts as a conversion table. So this transducer moving here really is a mimicking how the interrupter moves inside the tank itself. So this is what we call like an indirect linear type measurement. Same thing on here. This is I believe a Siemens design here. And they have a linkage rod. The mechanism is on the other side here, and it drives all 3. There's this linkage rod coming down that drives all 3 of these interrupters. And so you're hooking on the end of that. And once again, this is moving back and forth, and it's an indirect linear measurement because your actual motion is going 90 degrees perpendicular to it. One thing I'll mention is this is actually a medium voltage vacuum circuit breaker. And once again, because the vacuum circuit breakers have such a small travel distance, you have to get a smaller transducer to fit in and work with what you have. And if you see here, they actually have a stud mounted here. And so you can hook right up, and this is just a custom bracket that was made for it. But as the mechanism drives this back and forth, you got a pivot point here, and this actually goes up and down with the vacuum bottle here. So you're measuring the exact stroke of that vacuum bottle as you're operating the circuit breaker. The next thing we'll see is rotary trans. The nice thing about rotary transducers is they're very simple to, generally very simple to hook up and connect. The problem with them is now you're measuring an actual rotary motion in degrees, and you need to somehow translate that back to a linear motion. So you'll need something called a conversion table, which I'll talk about in just a little bit. And you'll see we have, there's a variety of different brackets and bolts to hook onto different styles of circuit breakers. But here's an example. And generally what I've seen, most live tank circuit breakers use a rotary type transducer. There's occasionally, like anything, I've seen ones where you use a linear type, but most people prefer to use a rotary type on your live tank. So they came up here, and this is your open-close indicator, but we can hook directly to there, and it rotates along with that circuit breaker so many degrees, and then however many degrees equates to a certain amount of millimeters in travel length. Here's an example of a dead tank circuit breaker where you're using a rotary. So here's this linkage arm that is connected to the mechanism, and it drives all three interrupters here. But coming underneath, we hook in one of our bolt adapters. Once again, rotary you can easily mount with this universal arm and hook up and get that transducer stroke. One nice thing is this in this Alstom circuit breaker, and in their manual they tell you maybe 1.7 degrees, or 1 degree equals 1.7 millimeters, or 1 degree equals 2.4 millimeters, or something like that. They're very good about putting in the manual that conversion. Here's another one where we actually, you'll notice on this circuit breaker, we have two different transducers per phase. So we have one that's measuring contact travel, once again with a rotary transducer, and then this other one that's measuring the dashpot travel, or the dampening travel. This circuit breaker, or this mechanism, operates very fast, and it has this dashpot in there that has certain properties you need to measure and make sure it's operating correctly. So timing, basic operations and results. So what are we trying to measure here? We know where everything should be hooked up, but now we actually want to get some measurements. So the first thing, of course, is close. You usually get to your circuit breaker, it's open. So you go ahead and close it, and this is just really mimicking putting the circuit breaker into service. The definition of the close time that we're measuring is actually from when the closed coil is energized until the first metal-on-metal contact makes. So on a vacuum circuit breaker, these are those two plates touching. On an SF6 style breaker, we have arcing and main contact. This is the arcing contacts touching. Then your open time is basically the same thing, where now you're having you're energizing the trip coil, and from trip coil energization until the last metal-on-metal contact part, that's your open time. And of course, this is the most important operation that circuit breaker needs to be able to do. If there's a fault, it needs to open up. Something else you'll see is the close open, referred to occasionally as trip free. You'll hear dwell time. Real world condition, this is where the breaker closes in, it sees a fault, and trips back out immediately to clear it. And where we do, what we measure here is when you close the breaker, as it comes closed, as soon as that first metal-on-metal contact touches, you'll have, that's your time 0. And then you keep recording that, and the breaker might not even come all the way closed. It'll come back open, and then as soon as they separate again, that's your other time you measure, and the difference between there is your close open time or your dwell time. These are the most common measurements performed. But if you really want to be thorough, you want to go ahead and do your reclose operation, where maybe the real-world conditions, a lightning strikes the line, the breaker trips, clears the fault, closes back in, fault's gone, no problem. One thing to pay attention to here is you want to make sure your pulse times are long enough and that your reclose timer is set long enough so you don't do damage to the breaker. And then lastly, there's an open-close open, which some people test, not as many do, but this simulates now that the breaker, there's a fault on the line, it opens up to clear it, there's a short delay again, it'll close back in, and then if that fault's still there, it'll open again and trip out and stay in the open position until you can investigate or make sure the fault's cleared down the line. So what are we looking for on travel now? As I mentioned before, very important. You want to make sure you hook up your transducer, you're doing your travel trace. A few key parameters to check here are your stroke or total travel distance. So the stroke is from your resting position in the open position until the resting position when the breaker is fully closed. So the difference between those two is the stroke or the travel length of your circuit breaker. You'll hear something called penetration or wipe. This is where you measure from when you first make contact, so as it's traveling, where it first makes contact till the final resting position when that circuit breaker comes closed. So you want to make sure you have enough contact here so current's flowing adequately. Something you'll see is over travel, where now the circuit breaker travels past the fully closed position, goes up, and then comes back and comes to rest there. And so usually the manufacturers will give some kind of parameter that you have a maximum over travel of 5 millimeters or so, because if it's going too far, you might be doing extra damage to the interrupter and slowly busting it apart. Rebound. This is something you'll have when, now say if you over travel and you come back, you'll notice on the close operation there's no rebound. It just over travels, dampens out, and is fine. Now as we come back and we do the open operation, we're coming down through here, we have an over travel, and then it comes back and rebounds in here, and then finally comes to resting position. One thing I'll mention on this, so open position, closed position, open position. These three lines here are actually our timing. So we do a thin line is actually open. Then as soon as the breaker comes closed, it's a thick line. And then as it comes open again, it goes to a thin line. So this is a close-open type operation. One thing I'll mention here is velocity. Velocity is very important. Why you want to measure velocity is you might have a circuit breaker that maybe the trip coil is bad or something's wrong with the coil. So it might operate slow. Instead of operating in 20 milliseconds, it might take 50, 100 or something because it's bound up. But then once that coil releases the trip latch, as long as your velocity is okay, it'll have the energy to interrupt that circuit breaker. I'm sorry, to interrupt that arc. If you don't have enough velocity, you can have a problem where it's not timed correctly. You don't actually interrupt the arc, and the circuit breaker won't do its job. So it's not only important to check timing, but of course also velocity. One other thing, when you're dealing with velocity, you need to measure it in a certain range according to these speed calculation points. Generally, you want to put these somewhere in the arcing zone. You really care what's going on when that interrupter is interrupting the arc. And you want kind of a straight line there, a nice linear portion of the curve to measure on. And I'll talk about speed calculation points in just a minute or two. So here's just a few different examples. One of a close. This is a coil current trace. These are our three timing. Then you have your motion here, and you see we actually have the speed calculation points on there, and it's right in that arcing zone. Next thing, we have an open operation, so coming from the open position down to the, coming from the closed position down to the open position. We also measured some auxiliaries with this one. A close open operation, so now this is a very nice operation. It came closed, no over travel, no rebound, came back, same thing, a nice smooth operation on this guy. An open close, you'll notice it came open. That was fine, but then on the close we have an over travel there. And you'll see now as the time keeps extending as we go to these multiple operations, and as we go to an open, close, open, you'll see now the breaker comes open, does a close, and then eventually comes open again. So what do we need to think about when we're setting up our test plan? We want to talk about the measurement time. How long do we want to set up our measurement time here? So on your single operations, your close, your open, generally 200 milliseconds is fine. If you have an oil circuit breaker, you might want to extend that out a little bit. If you have any excessive vibrations, you might want to extend the time out to make sure all that's dampening out there. Pulse and delay times, when you have multiple operations, your close open, your open close, you want to make sure you're putting these delays in there and putting a long enough pulse so you make sure you're testing these reclose timers and these different functions of the circuit breaker. So just be aware, and generally the defaults in your analyzers will cover that, but it's always nice to be aware what those should be. Transducer conversion factor. We have both analog, digital type transducers, so you want to know how many pulses is a millimeter, how many pulses is a degree, or like a resistance value if it's an analog. And then one thing, as I mentioned before, is a conversion factor or a table. So if you have where now you're hooking up your transducer and it's not an actual one-to-one representation of the interrupter, you might need to say, okay, 1 millimeter is equal to 3 millimeters here. So 1 millimeter of transducer travel is equal to 3 millimeters of actual interrupter travel. And then, or of course, if you have a rotary, you really need to make sure you know how many degrees equate to how many millimeters so you can get your eventual stroke values and velocities in a distance type measurement. And then, of course, where it really gets complicated is when you don't have a linear relationship. And so now you might have a rotary measurement where the first 1 to 10 degrees, it's 1 millimeter per degree, and then 10 to 11 degrees or 10 to 15 degrees, it's 2 millimeters, and then it's 1 millimeter again or whatever. So you actually need a conversion table. This is something you would have to get from the manufacturer. Sometimes they're good about providing it, sometimes they're not. So speed calculation points, as I said, you want to look somewhere in the arcing zone in a linear portion of the curve, and really you just choose 2 different points, but you have multiple references. So you could say distance below closed, a distance below upper point, a percentage of stroke, at contact separation or touch, or at a time after the upper point. So the manufacturer, once again, should specify these, and you want to make sure you use the correct ones for closing, and there could be different ones for opening as well. So some rules of thumb here, and what I found is generally the manufacturer should define this. I found Siemens and Alstom to generally use contact touch in 10 milliseconds before for the close, contact separation 10 milliseconds after for the open. Mitsubishi is like for a close 10% of travel to contact touch, and open it's contact separation to 90% of travel. ABB, they usually reference like a below close and a differential, and really with them you need to consult the manual because I've seen a variety of points for them. If you can't find it, no speed calculation points given, I would use contact touch in 10 milliseconds before for the close and contact separation in 10 milliseconds after for the open. Oil circuit breakers, they generally would give you some reference in the manual, or you'll see an old test result, and those generally are a lot longer. They're not as much in the arcing zone. They almost go over more the total travel length of that circuit breaker. But if you don't know and have no reference, I generally go with the contact touch in 10 milliseconds before, and this is what IEC recommends. And really this has to do with it's a half wave. In the IEC world, we generally have 50 hertz, and so 10 milliseconds is 1/2 cycle there. So why do we measure motion? As I said, I think motion is very important and it often gets neglected. But it verifies the stroke of the interrupter, verifies the velocity of the interrupter. If the velocity isn't quick enough, there won't be enough energy to extinguish that arc. Verifies proper wipe, so there's enough connection for the current flow. And then, as I said, even on certain ones where you hook up to the dashpot directly, but even if you don't have that, you can get information about the dashpot from your regular travel and your contacts. If it's not damping enough, you can have over travel, and that breaker will eventually destroy itself. If it's over dampening, it could slow the interrupter down. It could, once again, not really have enough energy to interrupt that. And if there's something where it overdamps, there's excessive rebound, you could actually have a restrike where the breaker interrupts the current and then the current starts flowing again and the breaker doesn't do its job. Then, as I mentioned before, for arcing contact analysis, or SF6 circuit breakers, there's something called dynamic resistance measurement. If you're performing this, you want to make sure you hook up a travel transducer with it so you can get the actual length of your arcing contact. So I just want to give a quick example here of a circuit breaker that was timed, and all trip times were within spec. And there was a large over travel. When we actually looked at the transducer measurements, there was a large over travel on B phase and excessive velocity on B phase. So if I went out and I was just performing timing measurements, I'd see everything well within spec here. Everything's around 19.3, 18.3, so a total open time of 19.3 milliseconds, and really only a differential of 1 millisecond between phases there. So if I was just doing timing, I'd look at my results, say, hey, this breaker looks good, let's put it back in service. Well, they were actually measuring your transducer, or they hooked up a transducer and were measuring travel on this one. And when you look at the travel, you'll see once again, all the times are good. And then you have A and C phase have a nice smooth transition, no over travel, and they align perfectly. But you'll notice there's a large over travel here on the B phase, and the total stroke length is quite different as well. And then one thing I'll mention, the open speed here was 6.83 meters per second on the A phase, where the B phase had 9.35 meters per second. So they actually went through and they operated the circuit breaker again, standard practice. If you get a bad result, let's check it one more time. And so the breaker came closed and didn't come open on the next operation. And so when they went in internally to this, they found out that the breaker had busted apart on that last operation. So if they wouldn't have been doing motion measurements, they would have just assumed this breaker was good and put it back in service. But really, once they went in and they did the repair, they got the three curves a little bit more lined up here, did the repair, motion was fine, damping was fine, and they were able to put it back into service here. So, as I said, all three phase trip times were well within spec. Everything looked good. If they went through and they looked at the motion, there's that large over travel on B phase. Once they operated a few more times, B phase actually stopped working. But if they would have looked at their initial results just with the timing, they would have thought breaker's fine and put it into service, and it would have failed in service. So if no motion measurement was taken, this breaker would have failed in service. So I hope from this you've seen that kind of what to look for out there. The different types of breakers you can have, things to look for, a number of breaks per phase, number of operating mechanisms, so you know how many transducers to bring. If you do need to when you bring your transducer, do I need a rotary or a linear? How many, as I said, if it's IPO or gang. So you can choose the right test instrument, set up the correct test plan, and then, of course, allow yourself enough time to connect the leads and have some extra hardware to mount the transducer. One thing I always mention is with circuit breaker timing, really the whole setup is quite difficult. But once you get the results, you have the manufacturer data to compare to. You have three phases. You have a few different things to look at. And now that I've been doing circuit breaker, and when I started with Mager, I've picked up transformer as well, and it's kind of the opposite with transformer. I can go to any transformer, and I have the right amount of leads. I can connect, but analyzing is quite difficult. Circuit breaker, total opposite. I don't know how to connect until I get there, really, unless I've done it before. I have to figure it out when I'm in the field. So figure it out, connect up. Once I connect everything, really analysis is quite simple. And hopefully from my example and some of my comments there, you guys really think not to neglect motion measurements on your high voltage circuit breakers. So I'll just mention a few of our products. So we do, of course, manufacture time and travel analyzers, 3 different ones. Our first one's an Eagle. It's kind of your distribution, your lower end of the high voltage for like your OCBs. It's 245 kV and below. One thing to mention about this, it does 1 break per phase and 1 operating mechanism. So any type, vacuum circuit breaker, oil circuit breaker, gang operated SF6 circuit breakers, the Eagle will handle those. Then as you go up to higher voltage, 765 kV, this one, the TM1700, will handle 2 breaks per phase or less. It can deal with gang operated or IPO circuit breakers. So oil circuit breakers, that's a 6 vacuum. One thing I'll mention, GIS, and regularly we have an option where you can do dual ground testing, where you time a breaker with both sides grounded. And then moving on, we have our top of the line, which is the TM1800 series, which is a fully configurable design here. This can test any breaker out there if you configure it right. We can up to 16 main, 16 resistor contacts, gang operated, IPO, oil, SS6 gas, GIS, air blast, dual ground testing. This thing, I've tested up to 765 kV myself with this, and no problem. So at this point, I'll put it back over to Year to see if there's any questions. You can see my contact information's on there. If you have any questions you want to follow up to me with an email, and we'll see where we go from there.
Okay. Robert, Gary asked that many manufacturers claim that it is not necessary to test motion in a vacuum circuit breaker. In your experience, is this true?
What I've seen with the vacuum circuit breaker is at the factory, they're measuring motion for sure because they want to look, a lot of times is for that rebound parameter where it comes, the contacts touch it, and it backs off. From a field perspective, I would say less people are doing the travel. They're at least doing the timing. And a lot of times the vacuum manufacturers, they'll give a spec where you can measure in the open position and in the closed position to get your total stroke length. I still think it's important, but a lot of times it's not always practical in there. And I always feel like manufacturers act like their breakers don't need to be tested at all. And of course, I work for, we make test equipment, and I was a field service engineer, so I believe testing is very important. But I would say it's still important, especially if you have circuit breakers that you've had failures on. There might be things you can pick up with travel that you won't see just in timing.
Mm-hmm. And Neil wants to know, is velocity important on a vacuum breaker at a distribution level?
I would say velocity, to an extent, yes. The thing with the vacuum breakers, they are such a small distance there. They're moving pretty evenly. It's almost like I would say within time, you should see that velocity isn't as important. But I would say the main thing why you would hook up travel is to look for an over travel and a rebound type deal on your vacuum circuit breakers.
Okay, everyone, we are running really close to time, so if we didn't get your questions, we'll follow up with you individually via email after the presentation. A copy of this presentation will be emailed to you in the next few days, and a recording of the session will be available on our website 2 weeks after the presentation. When we close the webinar, you would be redirected to a survey, and we will really appreciate it if you would fill it out and give us some feedback on how we can further improve our webinar series. Thank you, everyone, for attending, and have a great weekend.
Yes, thank you, everybody.